All right, welcome back. This is going to be the next installment for the series talking about what you can actually do to the driveline so that you feel the actual performance difference within the modifications you're doing to your car. For a previous example, I mentioned having a 350 horsepower engine and the things that you can do to the driveline to actually experience a better performance. Something you can feel in the seat of the pants and within your time slips, whether you're drag racing or circle track racing. So a viewer had sent in saying that they'd be more interested in this type of content, and it's something I know a little bit about. So we're covering this list of topics. So from the wheels and tires, hubs, bearings, brakes, spindles and axles, gear carriers, axle types, the drive shaft materials or lack of drive shaft, transmissions, clutch, flywheels, torque converters, and automatic transmissions. Pretty long list. But with the modifications in each one of these different categories, you can actually experience a greater performance gain in the seat of your pants than if you were to gain an additional 30 horsepower out of the engine. Okay, so you can, that same 350 horsepower engine that you have, by modifying these things, you can actually feel like you have a 500 horsepower engine underneath the hood. That is where the biggest performance gains comes from, is actually within the driveline components. Each one of those components has to match the type of driving that you're going to be doing or the type of racing that you're going to do. Because if you start lightening up some of the components and you're exposing it to the shock and awe of a drag racing car, say leaving the line at 5,000 RPM, that shock has to be absorbed through the components, the tires, so on and so forth. And if you're using lighter components like they do in circle track, you're going to grenade them like that. Okay, so we're going to go into the wheels and tires. Now, I should go without saying is that in order to put the power to the ground, you need to have the best traction. So depending on the type of rubber that the tire is made out of, the width of the tire, in order to create that footprint on the ground, and also the sidewall construction, whether it's a wrinkle wall drag racing tire, to be able to grow the tire patch on the starting line. But realize in drag racing and circle track racing, the tires are designed different than your standard radial tire on your daily driver. Your standard radial tire on your passenger vehicle is not going to deform that much. Okay, especially with newer vehicles that are utilizing low profile tires. These sidewalls are fairly short, so in order for that tire to transfer back and forth as it's going around corners, there's not a lot of give to the tire or the sidewall. They also don't wrinkle like a drag racing tire. They hold the form. So the tire diameter is going to be very similar from 10 miles an hour to that vehicle doing 200 or 140 miles an hour. The diameter is not going to change substantially with a radial tire. Now, some of the drag racing series, they have gone to the point where they have different classes for a big tire and a small tire class. Realize that even though drag racing classes use a bias ply drag slick with a wrinkle wall construction, some of them are making it mandatory where you actually have to run a radial drag tire. So the actual size of the tire maintains its shape. But the rubber that actually meets the road is going to be a very soft compound. Now, as I've talked about the transmission, gear ratios, so on and so forth, I've mentioned that your gear ratio plays a lot to the amount of acceleration that you can feel from the start or coming out of the corners in drag racing, how fast the power comes in so that you don't break the tires loose, something that you'll gain further down the straightaways or going into the next corner. Some of the radial drag tire classes are making it more difficult for the racers to actually go that fast. They're giving a, excuse me, I'm looking for the word. They're coming up with a not a deficit. They're coming up and creating actually a situation where people can't get the power to the ground utilizing a radial tire. Now, some of the classes will restrict the tire size to be factory size. So your 275, 50, 16s, whatever. They're introducing that to make it more difficult for the racers to be able to modify their drive lines. They're stuck to the parameters and the rules. Former or big tire drag racing, the tires actually become another gear ratio. So on the starting line with a wrinkle wall tire, when you're releasing the power, it actually makes the tire substantially smaller. So from the ground to the top of the tire, the diameter actually shrinks. So if you have a 411 gear ratio rear axle and you have a 30-inch tire, wrinkle wall tire, depending on the air pressure in the tire, that tire might drop to where it's only a 26-inch diameter tire. So the final drive ratio of your rear gear axle, say a 411, actually acts like it's a 513. Now, as the tire and the vehicle launches, as the RPM of the tire increase with the miles per hour going down the distance of the drag strip, they're actually going to grow because of the bias ply construction. It is not radial where it's holding its form. So you can actually have a drag tire that looks like an upside down mushroom on the initial hit on the starting line. But by the time you're going through the traps at the end of the racing strip, the tire might actually be 35 inches in diameter and be coned. So instead of riding on the entire footprint of the tire sideways, or say 2 or 3 feet long at the starting line, you're literally riding on a few inches of the tire. And the diameter of the tire has actually multiplied the gear ratio. Now, this was something that was learned very early on in drag racing. Let's go back again to the power glide groups out there. Realize power glides are not the traditional 3-speed transmission. They only have 2. But the power glide transmission, starting off with a very low first gear, multiplied the amount of torque that went to the tire in order to squat it down, use the entire footprint of the tire to accelerate the vehicle. Once it reached past, say, the 100-foot point of the drag strip, it was going into second gear. At that point, the car accelerated and continuously changed gears the entire rest of the drag strip. But it wasn't through the mechanical gear changes in the transmission. The transmission would actually be spinning faster than the tires were. But as the tires grow, they are multiplying the final gear ratio. So again, say that the drag car was equipped with a 488 rear gear ratio. Upon the starting line, it would act like a 513. But by the time you got to the 3/4 of the way down the drag strip, whether it's 1/8 mile or 1/4 mile, the tires are now 35 inches in diameter, and they've given the final gear ratio of approximately a 355. The tires themselves become a gear ratio. The most simple way to change your gear ratio is actually within the air pressure within your tires with a bias ply tire. So if you're cruising around town, say that you like to go to car shows, and you're in a location where the local law enforcement will let slicks slide on the street while you're at the car cruise, and you go out and do some of the Mexican racing, south of the border type things, you can cruise around with approximately 28 to 35 psi in a bias ply drag tire, and it's going to react just like any other tire. Obviously not on wet pavement, but it'll cruise around and feel like you're on a radial tire. But you can go into the parking lot or drive off the trailer, and you can drop your PS of your tire down to 10 to 12 pounds. You are changing your final gear ratio for a racing situation by simply an air gauge. Okay, so let's say that your tire is at 35 psi. Okay, your final gear ratio is whatever is in your rear end. So you say you have that 488. By dropping down to, say, 15, your tire is now changing the gear ratio the entire time it's racing. From the starting line, it's dropping it, it's creating a 513 gear ratio. By the time you have gone through the gear changes or through the finish line, your tires are now changing to like as if they were equipped with a 355 rear axle. Okay? And your reaction time, shift points down the drag strip, is going to alter when that gear ratio is introduced. So a lot of things within drag racing isn't necessarily the amount of output that the engine makes. The engine, on a consistent day, no matter if you're racing at 8 o'clock in the morning, high noon, or 8 o'clock at night, it might be able to produce a difference of 15 horsepower because of the ambient air temperatures. Okay, so say again that 335 to 350 horsepower. You can alter your gear ratio without having to take any axle apart, change the carriers or the gears themselves, just by changing the air pressure in the tires and the difference in gear ratio that you want to experience going down the drag strip. So depending on how much traction you need at the starting line and how much you want that tire to grow before you cross the finish line is all up to the driver to manipulate. If you know that with a radial tire that you are crossing the finish line precisely at the red line of your engine, say 6,500 RPM, and you're crossing the finish line, when you put on a set of drag slicks, you are not going to be crossing the finish line like that anymore. You're actually going to be crossing the finish line in most cases at 1,500 RPM less than your red line. Now you can alter that by putting more air pressure into your tires so they don't grow as much, and you can bring it back down, and balancing that throughout the time trials of drag racing. So let's say that you go to a weekend event and they have test and tune on Friday night so that you can at least see what your vehicle's doing, see the texture and stickiness of the track, see how your car is performing at altitude, adjust maybe your fuel ratio, and so on and so forth. During your time trials, work on your tire pressure for the most consistency, not only from the starting line to the finish line, but also when your shift points are occurring during the race and what you are actually crossing at the finish line. Because again, if you cross the finish line and you're only turning 5,500 RPM, but your engine's red line is 6,500 RPM, you're leaving 1,000 RPM out of the race. So even though you have a 350 horsepower engine at 6,500 RPM, you're not utilizing 1,000 RPM of it. You're actually crossing the finish line at approximately 330 horsepower. Okay? Where if you go the other variation or other direction, say that you switch from a small wrinkle wall drag slick to a radial tire that holds its form, and you have been testing and tuning with that drag slick and you've been crossing the finish line at 6,500 RPM, when you go to a radial, you'll be crossing the finish line at 7,000 RPM. Now you've left 500 RPM of acceleration out of the equation. You're not running the fastest the car is actually capable of doing. It's a balancing act that you will have to learn at every single racing event. Same holds true to circle track racing. Depending on the distance, the speeds that are achieved during the straightaway, going into the corners, the embankment of the corners, how tight they are, your tire pressure can determine how much tire patch you actually put to the ground. Now, for instance, if you're racing on a fairly flat track like Wisconsin International Raceway in Kaukauna, Wisconsin, very long straightaways, but the corners are very tight, and the banking is only approximately 15 degrees. So at the track in WIR, brakes are actually required. Okay, you have to slow the vehicle down, and the amount of brakes being applied to slow the car down for it to be able to handle going around the corner is completely different than if you run at Golden Sands here in Wisconsin Rapids or Plover, because even the straightaways are banked. So you're getting more traction, and the corners are longer to the point where your tires are being forced to the side all the way around the track. They never have a time to where they're running perfectly straight. They're always being flexed because of the friction and the G-forces of the vehicle pushing them over. You can alter and modify how the car is handling on the track just with a simple pounds per square inch of your tire pressure change. So depending on the ambient air temperature, the track temperature, the age of the tires, the weight placement, the suspension, it's all a gamble, and you have to be able to figure that all out. Like the example I gave is that this season, we're able to overpower our tires coming out of the corners at Golden Sands. We actually have to go to a higher gear, or excuse me, a lower gear ratio, so it delays when the power comes on full, to where we're not overpowering the tires coming out of the fourth corner, but in a straightaway, we're actually going to be faster. Okay. Now we're going to the next step of, now we're entering into the first corner, going faster. So how do we slow down even more? Again, that's done through tire pressure, rear suspension travel, so on and so forth. It's all something that nobody can come out and give you an exact science, because parameters change. Temperatures change, tire compounds change. Like for instance, this year we switched from Hoosier to the point where our rules now allow us to use American Racer. The tire compounds on the American Racer are a harder rubber than the Hoosiers. The Hoosiers, we could destroy them in one weekend. American Racer is warranting the tires for the entire season. Now we've gotten to the point, now it's like, okay, now we don't have the traction of the softer rubber tires. We have a harder rubber tire. They're actually a half an inch smaller in diameter. So it doesn't take as much power to actually turn them, and we have less traction. So now we have to delay the power being produced by that 350 horsepower engine to be able to accelerate the car for a faster time. There's going to be a lot more winter preparation for next season because everything's changed. And even between the classes, depending on how many cars are on the track, the amount of fuel you have in your gas tank. Let's say that you're preparing for a 100 lap feature. You're going to start out with a full tank of gas. There's a big difference between an 8 lap heat and the amount of fuel you have in your gas tank for the full race. You are now taking off almost 120 pounds off the rear tires just for the amount of fuel. Now that weight also affects the diameter of the tire, how much they squat down, so on and so forth. It's all a game that you have to learn. And anytime you're starting out with a new chassis, I don't care who you are, whether you're a NASCAR driver or team, to super late models, to sprint cars, ARCA series, IMCA series, when you get a brand new chassis, you have an adjustment period of time. Okay, you have to figure out what works, what's not working, and you have to modify parts if they are not fitting the package. Easy enough. Wheels and tires. Okay, we talked about the tire portion of it. Wheels, the rims themselves, also affect the performance of the vehicle. As the same as with the tire, the lighter the rim is, the more power can actually be transferred to the ground. Now, on most circle track conditions, because of the G-forces and the flex, because of the grip of the tire being transferred into a car, it's not only 2,400 pounds going up and down or being accelerated from the starting line. It's 2,400 pounds being exposed to one or two G-forces to the side when you go around the corner. So it's not only the amount of weight being pushed down, it's actually more weight to the actual car weight because of the gravity and G-forces that are forcing the car one direction when you're going around a left-hand corner. So again, most of your circle track cars are not equipped with aluminum rims because they cannot withstand the type of pressure that's being put on them. Okay, now could you swap on a pair of aluminum rims onto a circle track car and go for a few laps and last a little bit longer? Absolutely, you could. But the possibility of them breaking is increased. So most of your circle track cars are not equipped with aluminum rims. Drag racing cars. Now I'm gonna tick off a lot of the viewers of this channel. If you're utilizing some of the weld or some of the CNC'd aluminum rims offered by the part suppliers nowadays, they'll actually have their names on it, whether it be Summit Variation or Jigs or USA rims, so on and so forth. Realize they are an inferior metal. Okay, they're not going to be anywhere on par to the rims that are actually used in high-end racing. Even though they might say aluminum, the construction, the thickness, the strength of aluminum are completely different. Center force, let's take us back to the rims that I always used. Even in the same family of rims, center force, they had the Convo Pros. So during the 1970s, 80s, even into the 1990s, they had the pure aluminum original variations of the Convo Pros. In the 1990s, they started switching over to a thinner metal connected to a alloy, so not aluminum, a combination, and those tires were, or excuse me, just the rims were approximately 7 pounds lighter than the original Convo Pros that they used. The original Convo Pros could even be purchased for all-wheel drive or big trucks. So they could withstand the abuse of a heavy-duty equipment, but they couldn't necessarily take the shock of the release of power as in a drag racing application, where the 1990s through what they are still creating to this day, the Convo Pro design, they're lighter, they're stronger, and in my opinion, they look better in pretty much every car because of the way they're constructed and the materials used. Okay, so if you're buying some of the cheaper mimicking performance rims, don't expect them to actually be lighter or add performance to your car, even though you might be spending thousands of dollars for them. Trying to think of, because also in Sport Compact, tires are a little bit different too. Let's skip over that since we're talking about V8 type racing. Now again, circle track racing, they don't utilize aluminum in most cases. But if you look at your sprint cars, again, those cars are 1,600 to 1,800 pounds, pushing 950 horsepower, engines revving up to 9,000 RPM. They're using tires that are 30 inches wide on the backs, but you realize that they're also racing on dirt. So the amount of G-forces being transferred from the ground into the tire, flexing the rims is reduced. There's not as much traction, even with that big of a tire. Now, some of your big wing cars that are also racing on a hard surface, you'll notice their tire construction is totally different. They're actually using the late model variation hub, which utilizes an aluminum center section with a steel outer rim that actually carries the tire. The G-forces and flex of the tire is being transferred through the steel into a much thicker and more robust aluminum hub. Or, in some cases, again going to the sprint cars, there is no hub. The axle is a large diameter, some cases 3 to almost 4 inches in diameter. They actually have splines on the outside of the axle itself, and there is no hub. The axle goes straight through the center of the rim, and the rim actually has splines on it. It is not, there's no lug nuts holding the tire on. But once again, you don't want to necessarily be utilizing a sprint car that's being used in the dirt with these spline rims in a drag racing application. It's not designed for that initial shock or hardness involved with drag racing. It's meant for the sustained racing. Now, since I just mentioned it, we're not there yet, but spindles and axles, there's all kinds of ways to remove weight from the actual component of the axles or the spindles, or to, like I just used an example for sprint cars, they don't even run a hub. They don't use lug nuts. They don't use lug studs or axle studs. The axle is actually splined and the rim actually fits onto those splines, and there's one large wing nut that basically holds the tire on. They're eliminating weight. The brakes are not actually part of the axle. The brakes are actually on the drive shaft itself, or the yoke of the rear axle. And some of the late model cars, they don't even have a drive shaft. So the yoke is a direct coupler from the rear tail shaft of the transmission into the rear axle. There is no drive shaft. So again, what they are using in a high elite racing is making its way into even our daily drivers. Don't believe me? Look at the brand new Corvette. Rear engine Corvette does not have a drive shaft between the transmission and the drive axle. It's all in one. Okay, so what's used in racing, even at Formula One or NHRA Top Fuel, that technology makes its way down in production into our daily drivers, like the front suspension I mentioned from Ford, the strut. Pretty much every vehicle out there today on the road that's not a half-ton or three-quarter-ton truck is a strut front suspension. Okay. Other thing that I can add in with wheels and tires. Again, as I mentioned, some of them are connected to a hub. The muscle car era, they use a somewhere between a 3-inch to a 5-inch bolt pattern. Any of you that are trying to swap out tires, you need to know the bolt pattern of the axle that you're trying to mount the tires on. So whether it's a 4-inch, 4 1/4, so on and so forth. Now, in pretty much drag racing and circle track racing, in order to qualify at a certain time frame, so if you're going up from super stocks to a late model, your actual wheel studs have to go from that 5/8 diameter, or excuse me, half-inch stud to a 5/8 stud. And the stud has to be much longer. And they're actually looking at the threads to see how far they stick out from the lug nut or the actual design of the lug nut if they match the rim. Okay, in case you're using an acorn or a flat-faced lug nut, so on and so forth. Every racing syndicate has rules in place because they found out the strength is required. So if you're in drag racing, you're going faster than a 10-0, you are probably required to actually have the larger wheel studs. And they also have to stick out past the lug nuts themselves so that the inspections can see how much the threads are being worn out. Because it doesn't matter if you have a 1-inch diameter stud in your hub, if the threads are stripped out from being taken on and off all the time, the tech inspector is going to be like, no, fella, sorry, you got to leave. They're not going to allow you to race. All of that has come from accidents that have occurred. So pay attention to those kind of rules, folks. It will cost you more headaches, so on and so forth, but it is safety because they've proven that they will break. Now, circle track racing hubs. I had mentioned the previous ones I talked about using with the steel rims. Now, with the 4 to 5-inch bolt pattern on a typical high manufacturer vehicle, when you go into circle track racing, the hubs are actually replaced. Instead of just being the axle itself with a hub that's welded onto it, they go all the way through, similar to the connection of your sprint cars, where the axle just goes through and it's splined itself. Same thing occurs with super late model. Now, again, going back to the tire flex, with that tire flex being shifted back and forth, it has transferred through the rim. And of course, because the rim is attached to the hub also has to be reinforced. So your typical car going in a straight line, yes, you can snap the axles off right where the weld is for the hub. Circle track racing, the axle goes all the way through, and the entire length that the axle is going through the hub, it has a spline. And it also rides on two, just like in a regular car uses one axle bearing to hold the end of the axle in location. Super late model, the axle goes all the way through, and instead of counting on that one bearing that's approximately 3 inches in diameter, they go to two tapered 5-inch bearings that are sandwiched together. So the amount of twist and flex being introduced into the axle is shared between those bearings over a larger area. So what you guys are seeing in some of the late model cars, those hubs aren't necessarily there to reduce the weight. Okay, they're actually to strengthen the actual rear axle and the tires. Now, I'm going to close out this section of the video on this portion when it comes to tires and rims. Now, if this is a cross-sectional area of a tire, so your tire cut right in half, okay, the tire would mount, and this would be your bead. Okay, we have all heard in different situations where there's bead locks, so on and so forth. We'll get into that in a later video. That's for the tires, even with lower air pressure, say 10 to 12 psi, to where the tire has enough grip to stay with the rim, so the rim is just spinning inside the tire. Okay, that's basically all that's for. A little ease of operation when you're at the track, more grip to hold the tire onto the rim. That's all that is. It's not necessarily for a lighter wheel. Okay, just make that clear. Now, depending on your back spacing is where the intersection of your rim is being constructed. Now remember, if you're doing like a Pro Street car with a deep dish rim, say that you have 0 offset. And it's connected to the axle at the hub. Any pressure that's being applied to the outside of this tire, whether it's from the pavement or the tire being rolled over and growing in a drag racing situation, it's causing flex onto the rim. And that's being transferred to the rim to the hub or to the axle itself. The greater that distance, the more stress and flex is being put on the weld of the actual axle. So on the initial start of a drag racing car, when the power is all being introduced, depending on the radial or bias ply tire, the amount of shock that the tire can absorb from that is obviously more advantage towards a bias ply drag racing radial. But again, if you're going to a low profile radial tire and you are still using the Pro Street deep dish rims, you're going to realize really quick how much pressure is being put on the axle and how easily they will snap. Take it from experience. Now, in order to run that type of a deep dish rim design, typically your axle has to be shortened. So within the weight of the axle itself, the axle housing and the axle, by narrowing the rear end, you are reducing the weight of the entire package. So again, with lighter rims, a shorter axle, the amount of compression and sprung weight that the suspension has to absorb or control is reduced. But realize it also makes the rear axles weaker because of the forces being exposed to the exterior of the rim. That was the big practice during the Pro Street era of the late 1980s into the 1990s, that deep dish tire. What we have found through sport compact cars, believe it or not, the sport compact industry, is that we have gone to the point where the axle goes all the way to the exterior of the rim. So now, in order to make the axle a little bit stronger, it's extending all the way to the exterior, the outboard portion of the rim. The tire might still be as wide, but the axle is going through. Now, even in that situation, if the contact that's going on the inside of that rim is being transferred to the flex of the end of the axle, and it could snap the axle. In the outboard condition, though, you are sharing more of that force further in on the axle. Instead of being shared right at the hub, at the weld point, it's happening more, approximately 6 inches into the axle itself. That's where they'll actually start to twist and break. Either way, either catastrophe would lead to a crash. So are either one of those answers or either one of those options the answer to the problem? The ones that actually have the best design, and it's something again taken from NASCAR. Even if you look at the new 6th generation NASCAR, they're moving the hub connection point to the outside. And they're actually using aluminum. Okay, they're using a composite alloy. It's not pure aluminum. Okay, so they are designing the rims more for the impact purpose. So if the cars do crash, are those wheels breaking off and going into the stands? They're not necessarily there for the most competent strength within the design. But if you look at the NASCARs of, the 1960s through the mid 2000s, you realize they use steel wheels, and they also used a centralized back spacing for the connection point. Now those cars obviously are being exposed to the sidewards G forces going around the corners and the weight of the car going up and down. The central location allows the pressures from the exterior of the tire to be shared more evenly onto the um, axle hub itself. Okay, now the most advanced and most controlled axle design for control of the tire for sideways motion is actually your super late model car, circle track cars, utilizing that large hub. The double 5-inch or 4-inch bearings and the spline axle carrying the entire hub. That's actually the most beneficial to no matter how much force is being given to the exterior of the tire, it's being shared over a larger portion of the axle and not concentrated on one area where the welds are connecting the hub to the end of the axle. Okay, so in 9 times out of 10 in the situation, the best way to actually mount whatever kind of tire you're using is one with equal back spacing. So if you're using a 10-inch tire, it'd be a 5-inch back spacing. If you're using a 15-inch tire, it should be a 7.5-inch back spacing. It's that simple. Okay, that's the most safe way to do it. It's going to be it's going to allow the axles to handle more of abuse. Now, when it comes to modifying, well, I'm getting a little long here. I'm already starting to move on to the other topic, so we're going to end it there at the wheels and bearings. I didn't talk a lot about the bearings, but again, like I said, the hubs of circle track late model cars, they utilize 2 bearings, and it shares the weight, so the rolling resistance is reduced, the amount of flex in the tire is more controlled, and it's also made out of a heavier duty aluminum, so it does lighten the mass a little bit more instead of using an entire steel wheel. And because of the bolt pattern being increased from that 4 to 5 inches, they're actually at 8 to 10 inches. So again, that shear flex that's being introduced into the axle is shared over a greater area, and inside of that hub are much larger bearings over the traditional factory axle that just uses one axle bearing. A little bit more resistance, rolling resistance with a single bearing. Either case, having a centrally located back spacing will give you the strongest condition. For straight line use, a good aftermarket alloy rim is the best way to go. You can get away with the aluminum ones, 1,000 people have, but they're not as strong as the alloy. Steel are going to be still the strongest, but they add more weight. So anything you can do to lighten the rotating mass and reduce the friction, you're going to see more power in the seat of your pants. So closing out with this, if you have a 1985 Camaro, I don't know why I keep picking that, and it's equipped with American Racing steel rims that some high school kid threw on it because that's what he could afford, and you went back to the factory SS rims, are you going to necessarily feel the performance on the ride of the car and in the performance? It's right on the verge where you could probably feel a difference in the ride. As far as your quarter mile performance, depending on the driver, you might see a little bit of an advantage. But if you were to actually take those off and put on the light Convo Pros, you are going to feel the difference in the ride, the acceleration, and the performance of your vehicle. You're literally reducing the weight of the rotating mass by half in most cases, even from the factory SS rims. Okay, so hopefully it helps out. But remember, axle width and the location of your back spacing to create the strongest rim for the situation that you're going to be using it for. Even you sport compact guys can take this advice too. So whether you're going left and right around cones or on the road course, you still want to have that centrally located back spacing within your rim design. Have a good one.